All right, this is Unit 6, Lesson 2, and we're going to take a look at LeChatelier's principle. And we know that if we have a reversible process in a closed system, that will inevitably get itself to equilibrium. So we know that what equilibrium looks like is that the forward and reverse rates of reaction will become equal in rate, and that the concentrations of reactants and products will remain constant when we're at equilibrium. And as a result of that, we have this constant ratio of products over reactants at a given temperature. And we know that happens for any system, whether I start with reactant amounts only, we'll start forming products, reverse reaction happens, we get to equilibrium. If I were to start with just product amounts, that happens, get to equilibrium. Or if I have a combination, if I have reactants and products in the container, again with this reversible process, closed system, given temperature, the reaction will naturally bring itself to equilibrium. So when we look at LeChatelier's principle, all that we're doing is saying, well, what happens if equilibrium is disturbed? What if somebody comes along, and we refer to these as stresses, what if somebody comes along and changes the reactant concentration? What if somebody adds more reactant to the container? What will happen? What if somebody removes some of the product from the container? What if somebody changes the temperature? Then what happens? So we're looking at these systems that will always get themselves back to equilibrium, and LeChatelier's principle and these stresses that we're talking about are really just, what if we were to make the system not at equilibrium anymore? What if we change something so that we're not at equilibrium conditions anymore? What will the system do? Well, the system will get itself back to equilibrium. We know that. We know from whatever starting point, the system will always achieve equilibrium. And likewise, if I were to change any component so that the system is no longer at equilibrium, the system will naturally just get itself back to equilibrium. So this discussion of LeChatelier's principle is us assessing what effect making changes, causing stresses, will have on how does the system, what will the system do to get back to equilibrium. And the reason we want to talk about this is if I'm trying to force a reaction to happen, if I'm trying to force the production of extra products, it's very necessary to be able to manipulate a system that, well, basically when it gets to equilibrium, it's kind of stalling out. So we've, reached our max capacity of how much product we're going to make for the given conditions, and how can I change that? How can I make the reaction make more products if that's what I'm desiring to do with the process? Now, if we take a look at one thing I want to talk about that does not affect equilibrium position, it's the addition of a catalyst. So you notice if you read through the LeChatelier's principle statement, it says that, our stresses would be changing temperature, changing pressure, changing concentration. Adding a catalyst, though, well, what we talked about in the last unit, it can change the reaction pathway. It can give us an alternate pathway with a lower activation energy. So there's the catalyzed reaction, lower activation energy. As a result of that, that reaction will occur faster, so we can look at the slopes of these catalyzed and uncatalyzed reactions. You can see the slope is more extreme and therefore rates faster, this catalyzed versus uncatalyzed. So that's what we looked at in the last unit. That still all holds true, but in terms of what does equilibrium look like, catalysts don't really change that at all. So if you're given a question regarding, what does the addition of a catalyst do to equilibrium position, does it cause a shift left or right, it's basically not going to do anything to the equilibrium position. It gets us there faster, but it doesn't really change what equilibrium looks like. So that's an important thing to keep in mind moving forward. Okay, so going back to this LeChatelier's statement, again, if a system in equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. So I wouldn't worry about memorizing that statement necessarily, but rather just understanding what on earth it means. And so again, these systems will get themselves to equilibrium. If you change something so it's no longer at equilibrium, well, we kind of talked about this with the Q reaction quotient before, right? If I have a system that's not at equilibrium, I can figure that out, plug in my current values, see that it's not at equilibrium, and I can look at then, okay, well, do I need to make more products to get to equilibrium? Do I need to make more reactants to get to equilibrium? And that's all LeChatelier's principle is stating. So if I want to manipulate the system to force it to do something, like make more products, make more reactants, really we're looking at how can I predict, or using this using this principle to predict what's the reaction going to do in response to these changes. All right, so let's look at a very common reaction that is pretty important. This is the Haber process reaction, and I think we've seen this in many, many, many other examples before. So we're taking nitrogen and hydrogen and forming ammonia gas. And for this process, delta H, we'll throw that into the mix here, is negative 92.4 kilojoules per mole, just so we know that. And if we look at the equilibrium constant for this process, this is Kp. At 300 degrees Celsius, it's 4.34 times 10 to the negative third. We'll write that down at 300 degrees Celsius. Okay, so first of all, just looking at the value of this constant. Is this a big constant or a little constant? Well, that is a pretty small constant. So when I think about what does that tell me? Well, this value can be achieved by taking the pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed. And so this ratio, pretty small value, according to the Kp we have written there. So that means then that at equilibrium, if we're setting out to use the Haber process for the purpose of making ammonia, it kind of doesn't do that great of a job because we have a very, very small pressure, partial pressure of ammonia at equilibrium versus the partial pressures of my reactants at equilibrium. So that's kind of a problem. If I've purchased ammonia, I've purchased nitrogen, I've purchased hydrogen, I have my reaction vessel, I'm trying to make ammonia, trying to make a profit, and I put them all together and I get very, very, very little ammonia. That's a problem. So let's take a look at what LeChatelier's principle allows us to do. When we talk about increasing the pressure of a species or decreasing the pressure of a species, it's kind of the same thing as changing the concentration in the respect that, well, if I add more moles to the container, so let's say I'm going to add more moles of nitrogen to the container. This is at a constant size, this is in a constant size container. We're talking about this constant temperature right now of 300 degrees Celsius. So if I were to add more moles, I'd basically be increasing the pressure of nitrogen. And again, if I increase more moles, I'm talking about concentration, that's more moles per unit volume, so that's increasing the concentration. If I am just told that I increased pressure, well, the only way you can increase pressure for a substance in a container that's of a constant size and constant temperature is to add more moles of it. So those really statements both really mean the same thing, so we should get that about this process. Okay, so let's say that I add more nitrogen. Well, actually, let me scroll this whole thing up. And let's say that my equilibrium amounts. So at equilibrium, I have nitrogen, hydrogen, ammonia. So based on those constants I have above, let's say that I had 0.525 atmospheres of hydrogen. I have 1.575 atmospheres of 5.25 atmospheres of nitrogen, 1.575 atmospheres of hydrogen in there, and then I've got 0.0944 atmospheres of ammonia. So if I were to, again, plug all those into this expression for Kp, I would get that constant that we already stated, 4.34 times 10 to the negative third. Okay, so what happens if I want to make more ammonia. Okay, how about if I add some more nitrogen to the container? So let's say I up the pressure of nitrogen to 1 atmosphere. How did I do that? Well, I added some more moles of nitrogen into the container until I got the partial pressure of nitrogen to be 1.00 atmospheres. Okay, so if I were to plug that into the expression, well, if these concentrations plugged into the expression gave me a value equal to the constant, you can kind of see that changing one of those numbers, and only one of the numbers, I'm no longer going to be at equilibrium. So I'm going to put in the numbers, and what we called this before was the reaction quotient. So if I plug in non-equilibrium concentrations, which, again, now that the nitrogen pressure is changed, I no longer have equilibrium. Sorry, I said concentrations. I meant pressures in this case. So I plug all these values in, and I get a new value from the expression of 0.00228. Okay, so what we talked about before, right now, Q does not equal the constant, right? The constant is 4.34 times 10 to the negative third, and the Q value is, well, it's less than the constant, right? Because the constant is, if I take that out of scientific notation, that's it, right? So right now my system not at equilibrium. So if I plug in the amounts that I have, so if I added nitrogen, no longer at equilibrium, and now my current ratios have me at less than what the constant is. Well, just like the discussion that we had when we talked about Q, if my Q value is less than the constant, what has to happen? Well, that means that the denominator is too large and the numerator is too small. And so my reactants, which are in my denominator, are going to have to start forming products, and I'm increasing my product pressures and decreasing my reactant pressures. And so that will continue until my system gets back to equilibrium. That's the same exact thing that we talked about back when we talked about Q, except again, I came in and changed the condition. So I came in, added a little more nitrogen. What's going to happen? Well, what we would say is the system is going to alleviate the stress. How does it alleviate the stress? Well, it's going to use up the reactants that I just added and therefore proceed to the right. So you'll notice this wording again of the proceeding to the left, proceeding to the right, or shifts to the left, shifts to the right. So what that means is I have more reactants than I would at equilibrium, so my reaction is going to start making more products. And products being on the right side of the equation, that means that, again, we would describe that change as a result of this stress. In order for the system to restore equilibrium is to shift to the right or to make more products. Okay, so obviously if I wanted to make more products, a useful thing to do would be to add more reactants. That'll get me more products. However, that kind of costs a lot of money, right? If I keep adding more and more reactants, I'm making more products, but I still, in terms of ratio-wise, still have a pretty low amount of products that are being formed. So is there anything else that we can do? Well, again, making any of these changes. So if I increase something, if I increase a reactant, that will shift the reaction to the opposite side, right? So if I increase a reactant amount, that would mean my reaction is going to need to produce more products. If I were to increase a product amount, well, the reverse would happen, right? So if I increase this product amount, well, notice this ratio would be too large, Q would be greater than KEQ, and so the reaction would start to form more reactants. Okay, so the reaction, so in LeChatelier's principle, we say the reaction is going to, basically if I increase the pressure or concentration of something, the reaction will shift towards the opposite side. Right? So increasing reactants causes a shift to the right to produce more products. Increasing products would cause a shift to the left to produce more reactants. If I were to remove something, so let's take a look at, okay, well, how about my reaction is making ammonia, and I want to start siphoning off that ammonia and taking it out and getting that ready to, maybe we're going to sell it or whatever. I don't know if there's a black market for ammonia or wherever we're selling this. So let's say that we go back to our original scenario, and let's say that I start getting rid of this. So let's say that I change this ammonia. So I take some of it out so that I'm only left with 0.0012 atmospheres. So I remove some of the ammonia and reduce that amount. So, well, what would that do to my expression value here? Well, let's see. Q would now equal, we have the 0.0012 squared divided by the nitrogen, so that was 0.525. We've got the 1.575 cubed, and what that will come out to be is 7.02 times 10 to the negative 7th, and that is much smaller than the constant. So the reaction is going to need to, well, if I lowered this amount, I'm no longer at equilibrium, we've established that, and to get back to equilibrium, we have to replace what we took away. So the reaction is going to, again, be driven to the right. So it's going to shift to the right, and what that means is I need to make more products. To compensate for removing products, my system needs to make more products, and so we would say the reaction, again, shifts to the right to replace the products that we removed. So when I have a removal, it's doing the opposite thing as the addition did. So if I remove something, the system is going to produce more of whatever I took away. Okay, so if I remove a product, the reaction is going to be shifting to the right to replace and make more of the product that I just took away. if I were to remove reactant. So again, if I lowered one of these numbers, well, the reaction would then do the opposite. So if I lowered one of these reactant amounts, the reaction is going to need to replace them to get back to equilibrium, and so removing a reactant would result in the reaction proceeding to, or shifting to the left to replace the reactants that I took away. So again, we can see the application of understanding of the Q value and the, how does the system proceed to equilibrium. We can use that to help us make predictions. So again, if I wanted to drive a reaction in one direction or another for whatever reasons, I can do that by manipulating, removing things, adding things, whether that be, again, referred to as increasing pressure of something, or decreasing pressure, or increasing concentration, decreasing concentration. Another thing that you might see referred to is if I increase the overall pressure of the container. So different from increasing the individual reactant amount or product amount, or decreasing the individual reactant or product amount and partial pressure. If I'm talking about changing the total pressure of the system, that's going to have a slightly different effect than what we just talked about in terms of single concentrations of reactants or products. Everything's all moving at different times. So we look at this reaction. Again, if I were to, let's say I jammed this thing into a smaller container. So that would be basically by lowering the volume, we know that that would increase the pressure of everything inside the container. Well, that change as well would produce a stress, and as a result, the system is going to shift, in this case, to the side with fewer moles. If I increase pressure of the system overall, the reaction is going to shift to the side with fewer moles to lower the total system pressure. Likewise, if I increase the pressure, I just said increase pressure. If I decrease the pressure, the reaction will shift towards the side of the reaction that has more moles of gas. If I'm decreasing pressure, the system would want to restore that pressure by shifting to the side with more moles of gas. So that's another way of looking at these stresses that we can apply. Last thing I want to take a look at here is in terms of the value of the constant. All right. So going back to our reaction here, nitrogen plus hydrogen, and that makes ammonia. And so we have a Kp at 300 degrees Celsius, and that was equal to 4.34 times 10 to the negative third. And we know that the constant's going to be different at every given temperature. So if I look at the constant at 400 degrees Celsius, that's 1.64 times 10 to the negative fourth. Kp at 500 degrees Celsius is equal to 1.45 times 10 to the negative fifth. Fifth. Okay, so notice what's happening. If temperature is increasing, the value of this constant, is that going up or down? Take a minute, think about it. Well, negative exponents are increasing, so it's decreasing, right? So my value of my constant decreases when I increase temperature. So the other stress that we need to talk about is what energy does to, changing temperature does as a stress. And so notice on the other slide I said that delta H equaled negative 92.4 kilojoules per mole. That means that this is exothermic, right? So the energy term would be a product. That means that this amount of energy is kicked off when this reaction occurs. So that means that my reactants had more stored energy than my products. So energy is released as a result of this process. So if we notice what's happening, by increased temperature, well, the constant's decreasing. So that means then that this ratio of pressure of product divided by the pressure of reactant is decreasing. So that means then that by increasing temperature, I am decreasing the amounts of products that I'm going to see at equilibrium. So when we look at what that tells me, when I look at the stress of increasing or decreasing temperature, depending on whether the system is endothermic or exothermic, we're going to notice that changing temperature will affect the reaction in a different way. So in this case, if I increase temperature, well, we can kind of treat the energy term here as a product, because we said it's a product, it's produced. So increasing temperature, just like the increase of any other substance, like we talked about increasing the product concentration, it's going to drive the reaction towards the opposite side. Notice increasing the temperature drives the reaction to the left, right? So, because we can see this ratio changing of products over reactants, the number's getting smaller as temperature increases. So if I increase temperature, that's driving my reaction to keep more reactants unreacted and leave us with fewer amounts of product. And so we also then, with LeChatelier's principle, can recognize that the energy term also can be treated like any other reactant or product. So if I increase temperature, it's going to drive the system away from the side where the energy is. Because if I increase temperature, I'm adding energy to the system. Well, in order to use up that excess energy, what do we see the reaction doing? This reverse reaction is going to use up energy. The reverse reaction is endothermic. The reverse reaction is going to use up excess energy that has been introduced into the system, and so we see the reaction shifting to the left as a result of that. If the energy term were on the left side, so if the forward reaction were endothermic, then we'd see the opposite happen, right? Increasing temperature would drive the reaction to the right, produce more products. So again, we're going to treat increasing or decreasing temperature. It's the same idea, same concept as increasing or decreasing an amount of reactant or product. We're just looking for what side of the equation is the energy term on. So likewise, if I were to lower temperature, well, again, we see this trend going back as temperature decreases. That means I'm going to see more and more product formed. And so just like we saw with decreasing concentrations or decreasing reactant or product pressures, if I were to decrease temperature, I'd see the reaction driven towards the side that has the energy term to replace or reproduce the energy that's being removed as a result of temperature being lowered. So, and we can treat energy the same way in predicting what the change in temperature will do to equilibrium and to the system to return to equilibrium, and that's what LeChatelier's principle is all about.